Previously on Chemistry Z. Our heroes discovered the arrangement and motion of the particles in solids, liquids and gases. They also saw the different names for the changes of states from one state to another. And when all was looking well and good, they were ambushed by a heat curve. But by believing in their own source, they leveled up and were able to understand that melting and boiling point involved the breaking of intermolecular forces. But now, our heroes have encountered the deadliest concept thus far: ionic bonds. Will our heroes be able to pattern the dots and cross diagrams? Will they be able to do this? Find out in today's episode of Chemistry Z. Here are the retrieval questions for this lesson. You know what to do. The relative atomic mass for sodium is 23. Remember that the mass number is the large number on the periodic table. Therefore, the relative atomic mass number for chlorine is 35.5. The relative formula mass for sodium chloride is 58.5. If you need help with chemical calculations, check out this playlist where I go for all the chemical calculations that you need to know for GCSE. To deep ionic compounds, we need to refresh our memory on the atomic structure. In this video on the history of the atomic model, we saw how the contributions from J.J. Thomson, Rutherford and Chadwick brought us this atomic model.
I risked my life.
Just by looking at the structure, we can identify what element this is. It has 2 electron shells, which means it's somewhere in the second row of the periodic table, the second period. It has 4 outer shell electrons, that means it must be in group 4. And then if we do the coordination from there, we find out that must be carbon. We can double check this as well. Carbon has an atomic number of 6, which means it should have 6 protons. We look at this atom and it has 6 protons as well. So this is an atom of carbon. It has equal number of protons and electrons. Ions are atoms or group of atoms with an electric charge. Let's use lithium for an example. The charged particles inside are protons, which are positively charged, and electrons, which are negatively charged. In this atom we have 3 protons and 3 electrons, and so the overall charge is 0 because both of them cancel each other out. But if we add an extra electron, we now have 4 electrons, and so our overall charge now is -1 because we have 3 protons to cancel out 4 electrons. We have a charge of -1. Whenever you draw charged particles, you need to draw square brackets around and write the charge on the right hand side top corner. The brackets just show that the charge is all around the particle. This is what happens when we add electrons. We form negative ions. Negative ions are also called anions. But if we've removed electrons, things are different. We'll still have 3 protons, but now we have 2 electrons, and so the overall charge is +1. That also means that we have to change the bracket to a +1 charge. This is what happens when we remove electrons. We form positive ions called cations. You can tell if a substance is ionic instantly just by the presence of brackets. Alright, now we can move on.
What is this one again? Johnson, so what is this one again?
It's a sodium atom. Because the nucleus has 23 particles inside it, it would be looking mad complicated if I showed you what the nucleus actually looks like. You should be able to use the periodic table to work out the number of protons and neutrons it has anyway. But here we have 2 challenge questions for you to have a go at. Remember that since sodium is a metal, it's going to lose electrons and not gain electrons to complete its outer shell. Well, before the reaction we had 11 protons because that's our atomic number. Therefore we had 11 electrons to form a neutral atom. It's easier for sodium to lose one outer electron than to gain 7 new electrons to form its outer shell. Now we have 11 protons, 10 electrons, and so an overall charge of +1. This means that we've formed a cation which can attract negatively charged particles. Since we have changed the number of electrons, we have also changed the electronic configuration. It was 281 before, but we got rid of that outer electron, so now it's 28. If you remember from my video on noble gases, this is a configuration of the nearest noble gas to sodium, which is neon. The issue with using dot and cross diagrams like this is that the electrons are just jamming in one location, but in real life they're actually moving around. Also, you can't see the forces of attraction. Now try and do the same for aluminium. Just follow the steps that I showed you before. Before the reaction we had 13 protons. That's because our atomic number is 13. Therefore, we have 13 electrons to form a neutral atom. It is easier for aluminium to lose 3 electrons than to gain 5 new electrons to complete its outer shell. So now we have 13 protons, 10 electrons, and so we have a charge of +3. This is a cation that will attract negative charges. The electronic configuration was 283 before, but now it's 28, the same as neon again. We've got the metals on lock now. Let's have a look at the non-metals. Here is the setup for oxygen. Think carefully about what needs to happen here and have a go. Before the reaction we had 8 protons because our atomic number is 8. Therefore we had 8 electrons to form a neutral atom. It's easier for oxygen to gain 2 electrons than to lose 6 electrons to form a full outer shell. That's why these are called dot and cross diagrams. You either use dots or crosses to show the different electrons. In this example, the dots are the electrons from the original oxygen and the crosses are the new electrons that came from elsewhere. So now we have 8 protons, 10 electrons, so we have an overall charge of 2-. This is an anion and will attract positive charges. The electronic configuration went from 2,6 to 2,8. Same as neon again, but don't think that means that all ions have the same configuration as neon though. Let's do one more.
You're joking. Not another one? Oh, for God's sake, I can't stand this.
It's only a little old chlorine. You can do this. Before the reaction we had 17 protons because our atomic number was 17. Therefore we have 17 electrons to form a neutral atom. Chlorine gains 1 electron, so now we have 17 protons, 18 electrons, and so an overall charge of -1. This is an anion that can attract positive charges. Our configuration went from 287 to 288, which is the configuration not for neon this time, but for argon, which is another noble gas. When oppositely charged ions are formed, they attract each other due to the electrostatic forces between them. Remember that these charges are spread all around the ion. That means that millions of ions can join up, making a giant ionic lattice. Ionic lattice could be represented like this as well.
Please, I don't have any time for any gossip now. Eh? Yes.
Look at it.
Don't start panicking. They are both showing the same thing. Notice that you can see the oppositely charged ions in both diagrams. This tells you that you've got an ionic compound. Because ionic compounds have strong electrostatic forces acting in all directions, a lot of heat is needed to break all of them. This is why they have relatively high melting points.
I have the power!
A limitation of using these two models is that it doesn't show the ions vibrating in a fixed position, and the forces of attractions aren't physical objects. Just like magnetic fields, you experience them but they're not objects. That's the same, it's kind of the same thing here with these electrostatic forces. Oh yeah, you're also meant to be able to deduce the empirical formula of the lattice structure. It isn't that deep. You don't need to calculate anything. I did the empirical formula calculations in this video and you can go check those out, but here we just have to look at the image. For every 1 sodium we have 1 chloride ion. So the ratio is 1:1. It's a 1:1 empirical formula ratio. It's as simple as that. I've got some challenge questions for you now. Pause the video and try and answer each one. Aqueous comes from the Latin word for water. If something's aqueous, it's dissolved in water. That means that B is the answer to the first question. The reason is because we can see water particles in the image. Whenever you see that Mickey Mouse looking structure, that thing there is water. The one that electricity can flow through is B. This is because the ions are now free to move around. In A, they're solid, so they only vibrate in a fixed position. They can't move throughout the structure. Another way to get ions flowing in ionic compounds is to melt them, so turn them into a molten substance. Here's a past paper question.
Jesus Christ.
You've got this, it's cool, it's cool. The diagram shows magnesium and iodine atoms forming magnesium iodide. Only the outer electrons are shown. The dots and crosses represent electrons. Use the diagram to help you answer this question. Describe as fully as you can what happens when magnesium reacts with iodine to make magnesium iodide. To gain full marks, you should use the word atom, electron, and ion in your answer. This is actually a describe question for 4 marks, but let's imagine that it's an explain question for 6 marks. You can bullet point your answers if you want to. The magnesium atom has 2 electrons on its outer shell. These 2 electrons are lost to form a magnesium 2+ ion with a complete outer shell. Each iodine atom has 7 electrons in its outer shell. Each iodine atom gains 1 electron from the magnesium to form a -1 ion. The oppositely charged ions are held together by electrostatic forces, acting in all directions, forming a giant ionic lattice structure. Another common thing examiners like to do is compare ionic and covalent compounds, but we'll do that in the next video. I've got another activity for you.
What nonsense is this?
I promise, this is the last one, I promise. Look at the table. What do you notice about the melting and boiling points for ionic compounds? Sodium chloride and magnesium oxide are the ionic compounds here, and they have very high melting points and boiling points. And here is why. This is a perfect answer to a question asking you about why ionic compounds have high melting and boiling points. Firstly, the electrostatic attractions are acting between oppositely charged ions, and these are strong and acting in all directions. Therefore, a lot of energy is needed to break the bonds, leading to high melting points and boiling points. And there we go. Lesson done.
Fatality.
Check the description for the revision flashcards that I've made, and also the revision timetable. Use the timestamps to jump from one location to another that you need to look at again, and I'll catch you guys in a bit.